Here we're going to look at confidence intervals for P, a population proportion. In the past, we used the sample mean x bar to estimate the population mean mu. Now we use the sample proportion p hat to construct confidence intervals to estimate the value of a population proportion p. So instead of using x bar to estimate mu, we're using p hat to estimate p. Suppose we want to know the percentage or proportion of CCC students who have a tattoo. Over the past several semesters, a survey has been given to a sample of CCC students. The question, do you have any tattoos, is given as part of a voluntary survey. Of 300 students who answered the survey, 120 respondents said they have a tattoo. Notice the question, do you have a tattoo, is really a binomial. Either yes or no are the only possible answers. So you either have a tattoo or they don't. If we want to estimate the proportion P of all CCC students with a tattoo, what is our best estimate? Well, our best estimate so far will be what happened when we took the sample. So they told us in the sample that 120 said they have a tattoo out of the 300 that answered the survey. So our best guess right now for the percentage or proportion to have a tattoo is 120 out of 300, which is 0.40. Since we only had a sample of CCC students, we must be aware of a margin of error. If we repeatedly take samples of size 300, the standard deviation of the sampling distribution of sample proportions would be sigma sub p hat. So the standard deviation of the sample proportions equals the square root of PQ over N. So for us, the standard deviation of the p hat distribution of the sample proportions would be 0.4 times 0.6. Okay, the 0.4 coming from right up here. 1 minus 0.4 is 0.6. And then divided by the number in the sample, which was 300. And we get about 0.0283. Okay, so here I just show you the idea that you take the standard deviation of the binomial, which is square root of NPQ, divide it by n, and that simplifies to the square root of PQ over n. Okay, now we just have a little bit of an issue. We're trying to estimate P, so we do not know what P and Q are. Therefore, we use our sample statistics, P hat and Q hat, for P and Q. So because we don't know what P and Q are, because those will be the population parameters, we have to use P hat and Q hat in their place. Okay, so we now may construct a confidence interval for the proportion of all students with a tattoo who take classes at CCC. We always use Z star because we know sigma for the binomial. Okay, so the good news about when you deal with proportions, or P's, you will always use Z. You don't have to worry about the T distribution because we always know sigma for the binomial. So a 90% confidence interval. Well, how are we going to come up with that? Well, what we do is the same concept as before. If you remember before, when we did a confidence interval for the mean, we took our sample mean, which was our best guess for the population mean, whatever we got in the sample. That's our best guess. Then we add or subtract. How many standard deviations do we want to go from the mean? So that's your z-score. And then times the standard deviation of your distribution. That was when we had the sampling distribution of sample means. Well, now we're looking at proportions. So now what we're looking at is when we do our best guess plus or minus this margin of error. Now our best guess is P hat plus or minus the Z star value, so how many standard deviations from that center are we going to go, times the standard deviation of the p hat distribution, which was p hat q hat over n. Because we're, instead of pq over n, we're using p hat and q hat because those are the best estimates we have for p and q. Okay, so now it's just a matter of plugging in the numbers just like we've always have done. So p hat was 120 out of 300. Okay, and that was going to be in the next step 0.4. The z star value for a 90% confidence interval is 1.645. And then you have your p hat, q hat. So if there's 120 successes, there'd be 180 failures out of the 300. Okay, and then divide by your sample size 300. In the next step, I just put in the decimals. Now, this is one of those things that you don't want to round too much in the middle steps. 120 over 300 perfectly reduces to 0.4. Let's just say that was like 127 out of 300. Then you want to put that fraction in your calculator. Okay, you don't want to round these decimals too much until you get to the final step. Okay, but this one works out nicely where they do reduce to a nice decimal. Okay, so that's what I did here. Okay, so your margin of error is 0.0465, or about 4.65%. Add and subtract that from the best guess for p hat. And your interval, 0.3535, is less than p, is less than 0.4465. So now, rather than mu, a population mean, being in the middle here, p, your population proportion, will be in the middle. Okay, the 95% interval is the same concept. The only thing that's going to change is instead of 1.645 for the 90% interval, we have 1.96. Okay, so if you go through and do the calculations, I'm going to show the answer. Okay, so there's your confidence interval for p, a 95% interval. Okay, and what you notice is to become more confident, so 95% compared to 90, this interval is wider than the 90%. Because to be more confident, you have to allow more values into your guess. Okay, so at the very end here, it's essential to understand that we're using a sample statistic to estimate the true value of a population parameter. Since we use p hat to estimate p, we must be aware of that margin of error. If we chose a different sample, then we may get a different value for p hat, and therefore a different interval estimate. In our example, we made an interval estimate around p hat where we hope our interval contains p. And this is the exact same concept as using x bar to estimate mu. If we chose a different sample, we might get a different value for x bar, and therefore a different interval estimate for mu. But again, the concept is exactly the same. It's just now we're dealing with proportions, percentages, rather than means. So to construct a confidence interval for p, for a population proportion, we need to have n times p hat and n times q hat be large enough, and we classify that as being greater or equal to 5. And again, sometimes you'll see that as a 10, but the book that we use just says 5. And then the endpoints of your interval, your best guess for p is p hat, and then you add or subtract your z star value, which is the number of standard deviations you're going from the middle, times the standard deviation of your distribution. Okay, so that's how you construct a confidence interval for p.